clearing them. And all right. So, first things first, grab your data sheet. That's the 2-pager I gave you guys first. The very first data set is extraordinarily tiny. It's extraordinarily tiny. I think it's 2 sentences, maybe 3 sentences long. 4 sentences long, I'm a liar. It says single proportion testing, so make sure you look at the pages in the right order. It says single proportion testing. Suppose 12% of people normally get the flu. Go ahead and read those few sentences right there.
That's what you mean by working.
Yeah.
Good, good. So, that's a fantastic, trained you guys well. Very critical thing, what does it mean by working? Let's define that. So the first question, Andre, may I grab a template sheet?
Yeah,
this is so new, I haven't memorized yet, so I want to make sure. So I'm going to have a template sheet to make sure that I have the same thing you guys do. So, does the vaccine appear to be working? Michael says define what we mean by working. Define working. Let's define it right now. Kate's got a very strong definition of working. Nobody gets sick. That's strong. And that's ideal, yes?
I was taking it as on the individual basis of is it working?
Oh,
that individual doesn't.
Good.
But there's different strains.
JC, let's suppose they targeted a strain. Good for you. There are different strains. You might remember H1N1 was all the rage. It was the in vogue flu a few years ago. But more people got sick from the normal annual flu than the H1N1. Let's assume they've targeted a strain. And the strain they've targeted gets 12% infection. So let's suppose we've minimized that variable, okay? Thank you for that. That's a good point, though. Dan?
Is it 12% of people who normally don't get the shot?
Correct.
Okay.
The flu infection rate for those who don't get the shot is 12%. So roughly 1 in 8 people are going to get sick with or without the shot. Thank you for that. That's going to be your null distribution, is that 12%. So those curves we kept drawing last week, there's your null curve right there. Your null curve, put that on the board right here. So this is 12% is right here. This is people who get the flu. I'm going to put without the shot, but it could be with or without the shot. In other words, the shot has no effect on them, and 12% is the flu rate. But with the flu without vaccination. Or if you want to look at it a different way, Deanne, with the old vaccination. You can also look at it that way. These people are making a new vaccine they want to prove is better than the old vaccine, so it's working better, which we're getting close to defining what we might talk about by working. It's very important, very important. Stacy?
I'm just thinking 101 is 10% of the 1,000, so
Good.
12% of people get the flu normally without the vaccine, and 10% of the people. So it's only, if it were that, it would only be working by 2%. I mean,
So we need to figure out if it's statistically working
Yeah.
or practically working.
yeah.
I wish I could just can that whole conversation right there and just put it on a shelf for the world to crack open. Did you hear that? The whole discussion that just happened? They started with 12%, which is your null center of this curve. And this is the center of the curve. That curve has a curve with it as well. We've got 1,000, a sample size of 1,000, which is far larger than it needs to be to guarantee there's actually a bell there. We know that it's definitely bell-shaped at that point. Fantastic. So then we send out into the world, we get this 10.1% result from our sample. So here's, if you will, I'm going to call that in quotes, little p, because that's essentially the proportion that people that get sick. People get sick at 12%. And then we go out and give 1,000 people this vaccine, and 101 of them get the flu, yes? Which is 10.1%, which is where with respect to 12? It's left of it, yes? Now the question is how far left? I don't know yet. That's where the math comes in. The math will tell us how far left, which means it will tell us whether it's statistically significant, whether it's an outlier with respect to 12%, or whether it's believable to be on the curve. So the question is, somewhere over here is that 10.1%. We just don't know where yet. We know it's left. Michael's got that. We know it's left. So you got 10.1% here. Well, I'll do this here. 10.1% with a question mark because we don't exactly know where it is. That's our p hat, though. Our p hat is 10.1%. We know it's left of 12. The question is how far left of 12? How far left of 12 is it? How far left of 12 is it? That's what today is all about. Deciding. Because that little p-hat value carries a big p-value. And the big p-value tells us whether or not it's an outlier. And that'll tell us whether or not we think the flu vaccine is working. So the question is, have we decided? Oh, JC, go!
So what happens if we just get a little statement like this and it doesn't define what working is?
That's what right now, we got to make sure we're defining what the flu vaccine working
But
is.
we can define it, but we don't know what their definition is.
I guarantee that whatever we come up with is going to be what they're testing. What do you think they're testing? We've already established it right here, haven't we? What's their vaccine going to do? Is it going to stop it, or is it just going to? It's going to prevent it as much as possible. People still get sick on the flu vaccines, but we want them to get sick less. We want them to get sick less than without the flu vaccine. We can't guarantee we're going to eradicate the flu with a strain of vaccine. That happens every once in a blue moon. I think the polio vaccine, for that matter, doesn't even eradicate polio. I think it just knocks it down to essentially zero. But vaccines aren't designed to eradicate. They're just designed to prevent down so that you're better off than not having it. The question is 10.1% enough to write home about? Is it down far enough to be like, okay, now it's significant? We don't know that yet. We have to run a test to find out. Go ahead, Kate, you want to say something?
Oh, it doesn't really matter. I was just gonna say that kind of the whole point of vaccines, yes, is that you don't get the flu, but as well as it's building a barrier for those who are immunocompromised who can't get the vaccine.
Very nice, very nice. But by you bringing that up, you've bridged the gap usually between anecdote and statistic. You either do or don't get the flu, 0 or 1. But on average, a percentage of the population, no, of course, but the population has a percentage of sickness. You, 100% or 0%. We can't measure that with sample size of 1. I mean, we can, but it won't tell us anything. But if we look at 1,000 people and 100 of them get sick, and we've controlled for things like strain and prior condition sickness, then we get an idea of the average to see if something's actually working or not. This is how H1N1, you'll do this later on in a quiz or on your next exam. The H1N1, the old vaccine for that, they discovered that if they watered it down, it still worked. Worked means that it produced enough antibodies to fight the strain in most people. It wasn't worked in that it eradicated the flu across all those that got it. It's just fewer people got sick with it than without it. Renee, go ahead.
Does the lack of margin of error matter?
We're going to make it today.
Oh.
Did you hear this question? Does the lack of margin of error matter? There's no margin of error. And that's part of the question mark right here is where's the margin? We're going to make it today. The margin will show up today, I promise you that. And we'll really promise to that. We're going to make a one-sided confidence interval, so it's going to have kind of a weird asymmetric margin of error. Is that good? Fair? Other questions? Fantastic. Keep those coming. These are good questions. All right, let's start going through the template. Let's start going through the template. And this is going to be a little bit, this is new to me. Like I said, I just made this up over the Christmas break. I'm like, I think this is the next best step towards where we're headed. And some of this isn't going to sound like anything right yet because we haven't gotten to some of it yet. But I think this is going to be a good, anyway. So number one, what variable or variables are we testing? P or mu? Well, you know the answer to that. It's going to be P. You have to circle P. Boom. 1 point. Check. I think all your quizzes are going to be like this too. You just submit the sheet to me with whatever quiz is on the top of this. Nice. I'll make more copies of this so you guys have them around. Okay. Define the variable in context of what we're testing. Let me zoom in on this one here. So we know the variable we're testing is little p, yes? We know we're testing little p. So what is little p going to be? What are we interested in this study? Little p. Go with that, Tim.
I said whether or not if we get the flu rate.
So the flu rate, now I love the whether or not. That's a 1-0 again, but we gotta talk about an average, right? So it's the proportion or flu rate, I love that. Flu rate, flu probability, flu percentage, flu proportion, all the same thing. Use any of those words interchangeably. Is it okay if I just put flu rate, or flu, let's go with flu proportion. Proportion, just because that uses the same language of the section. The proportion of those getting the flu, what does that mean? What's this chimney flu? Which people getting the flu?
That were
The ones that got the vaccine. We're trying to see if the vaccine works. So we're testing those who took the vaccine. So it's the proportion of those getting the flu Right, after vaccination or with the vaccine. Stacy, I love the fact that you refer to the control group. We have to compare them to the control group, which is essentially the rest of the population, the 12%. The question is this proportion significantly different than that 12%? That's why I put P in quotes. We're assuming the vaccine's not going to work in the beginning. We're going to assume the vaccine's ineffective and try to be proven wrong, just like every other hypothesis test we're going to do. You assume the opposite of what you're trying to prove and hope that the opposite comes out. That hopefully that supports your cause. So there's our variable that we have to test. Now I'm watching the clock. It's about 5 after. Want to take 5? Get some air, get some water. You want to keep hammering through. What do you guys call? Nobody's calling.
5.
5! Boom, Harrison calls it. Take 5. Let's go through the rest of this template to make sure you understand what's going on with the template. We're going to see how to put that variable into work now. JC, what you got? Let me close this off here.